right, moving on to acceleration. Let's start with classifying as acceleration as a scalar or vector quantity. We know from our formula for acceleration that we need to use velocity, and if we're using velocity, which is a vector quantity, we know that acceleration would also be a vector quantity. In our own words, what is acceleration? We should remember from our notes on objective 1.4 that acceleration is a change in velocity. Now, everyday language uses the word acceleration to mean one thing, which means speeding up, but we actually know that acceleration can be three different things. Speeding up is one of them. We know slowing down is also acceleration, frequently called deceleration. And the last thing, since it's a vector quantity, any change in direction would also lead to an acceleration. So changing direction is the last way an object can accelerate. So speeding up, slowing down, and changing direction. You do need to know that for the test. So we have this formula, our big five formula for final velocity, which is final velocity is equal to initial velocity plus acceleration times time. We're going to manipulate this formula to solve for acceleration. So if we do acceleration, so let's copy our formula down. V is equal to VO plus A times t. Our first step is we want to get that velocity initial moved over to the other side. So we subtract it from both sides, which comes out to V minus VO is equal to A times t. And if we want to get acceleration by ourselves, we divide both sides by both sides by t, my mistake. And that cancels out the time over here. And our final formula comes out to be acceleration is equal to velocity minus velocity initial divided by time. And that velocity is actually a velocity final. If you look over here on this short piece of paper, you'll notice that in the key information that's not mandatory to know, the formula for acceleration is written the same as we've written it here. This is just to show you that our big five kinematic equation solving for final velocity and this formula are the same thing. I mentioned this multiple times in class that these formulas are derived from one another. You don't need to memorize this formula, however, knowing it might save you some time on the test. For 15, 16, and 17, it's actually having us calculate the acceleration experienced by these objects. So whenever we're approaching a problem, the first step that we need to do is make sure that we identify what we've been given in the problem. So if a car starting from rest accelerates to a velocity of 8 meters per second in 6 seconds, what is the acceleration the car experiences? So obviously it's telling us straight up that we need acceleration. But there are three other pieces of information that we need to calculate that: the velocity final, the velocity initial, and the time. Well, it tells us that our final velocity here, our v, is equal to 8 meters per second. And then we also have a time that's given to us. The only thing that's not directly obvious is the initial velocity. And that keyword comes from rest. So if it's accelerating from rest, our VO is going to be equal to 0 meters per second. We plug this into our formula, which a reminder is A is equal to V minus VO divided by T. So our acceleration is going to be equal to 8 minus 0 divided by 6. 8 is going to be equal to 8 divided by 6. When you do 8 divided by 6, you get 1.4. Let's do it. 8 divided by 6, which is equal to 1.33. So our acceleration is going to be 1.33, two numbers behind the decimal, and that's going to be meters per second. And our unit, because we had, let's do this, we have meters per second divided by seconds. The only way to get seconds up here is to, pause for a second. When you've got meters per second divided by seconds, it ends up being meters per second times seconds, which is meters per second squared. So meters per second squared is our answer. Let's do number 16. A ball with an initial velocity of 4 meters per second is brought to a stop in 1 second. What is the acceleration the ball experiences? So again, it's asking for acceleration. We don't know what that is. We know that it has an initial velocity, so a VO of 4 meters per second, and it is brought to a stop in a time of 1 second. If it's being brought to a stop, our final velocity is, you guessed it, 0 meters per second. So we do A is equal to 0 minus our initial velocity, which is 4, divided by 1. So A is going to be equal to -4, and this is the key here, making sure that that 4 comes second so we know that it's a negative acceleration divided by 1. Our acceleration is -4 meters per second squared. Whenever we have a negative acceleration, that is telling us that the object is slowing down. And if we look back at the problem, we know that this ball is being brought to a stop, therefore it is slowing down. Number 17, if an object starting from rest experiences an acceleration of 3 meters per second squared for 8 seconds, what is the object's final velocity? So we've been given 3 meters per second squared, which is the acceleration. We've been given a time of 8 seconds. And it wants to know what the final velocity is. We then need to be able to derive from our problem our initial velocity, and that comes from the wording. It says starting from rest, which means that our initial velocity is 0 meters per second. So there are a few ways we can do this. We can go back to this acceleration formula, but we also know that our big 5 kinematic equation is already set up to give us our final velocity. So I'm actually going to use that big 5 kinematic equation. V is equal to VO, 0, plus acceleration, which is 3, times time, 8. So V is going to be equal to 3 times 8, which is 24. And that's going to be a velocity, so it's meters per second. For question 18, 19, and 20, we're actually using this image. We're given this instruction that each line illustrates the path taken by an object. The speed of the object depicted above is constant throughout their travel. The reason we're using the word speed here is because if we think back, speed is a scalar quantity, so there's no directionality. So the magnitude of this object's velocity is constant. However, we know that the direction also plays a part in velocity. So we have to use those things in conjunction with one another to figure out how we would describe the acceleration of these objects. So number 18, why does the speed of object 2 not change even though the object changes pathways? So we actually just went over this one. I unintentionally jumped the gun on that one. When we look at object 2, the path changes, which means that our velocity changes because right here we have a direction change. However, the speed is staying the same, and that goes back to the fact that speed is a scalar, which means it doesn't consider direction. Which object has an acceleration of 0, and how do you know? Well, we know that there are 3 ways from our previous part of our sheet: speeding up, slowing down, changing direction. We know that both of these objects aren't speeding up or slowing down because the speed remains the same. So the only way that an object can have acceleration is if it changes direction. We just went over the fact that object 2 does change its direction. Object 1, however, keeps heading in a straight line. So the answer for number 19, which object has an acceleration of 0, would be object 1. The way that we know is because it travels in a straight line. And then finally, which object has a non-zero acceleration and how do you know? Obviously, that would be object number 2. And that is because it is not traveling in a straight line. All right.